Take a single speck of dust off a bookshelf, small enough that you would lose it in a sunbeam. In standard quantum mechanics, the mathematical object that describes that speck does not live in your room. It lives in a space with something like 10 billion separate directions in it, which is within shouting distance of the number of stars in everything we can see. One speck, off a shelf. And that object takes values that are partly imaginary. It has never once registered on any instrument ever built, and the theory requires it to add up to exactly 1, the way a set of odds does. Physics calls it a wave. It is the wave in every documentary you have ever watched about how reality supposedly does not exist until somebody looks at it. So is it a wave at all? And if it isn't, what has been there the whole time instead? Make yourself comfortable and let the evening go still. Subscribe if you haven't already, and stick around because the whole thing turns on a distinction almost nobody is taught. And once you have it, you will never watch that animation the same way again. Let's dive in. Part 1. The dots on the screen. There is a room, somewhere in a physics building, where the lights are kept low and the air is kept still, and the most famous experiment in modern science is running one particle at a time. The apparatus is not complicated to describe. At one end there is a source, an electron gun, essentially a heated filament and a set of charged plates that pushes electrons out in a thin, faint stream. In the middle there is a barrier with 2 narrow openings cut into it, close together, each one far thinner than a human hair. At the far end there is a detection screen, and behind that screen there is electronics sensitive enough to register the arrival of a single electron and record exactly where it hit. The whole thing is tuned down until the stream is barely a stream at all. The intensity is dialed so low that, on average, only 1 electron is anywhere inside the apparatus at any given moment. 1 electron leaves the source, it travels, it arrives. Then, and only then, the next one is released. There is never a crowd. There is never a beam in the ordinary sense. There is a single object making a single journey, over and over again, with an empty apparatus in between. Now watch the screen. The first electron arrives. What appears is a dot. Not a ripple, not a smear, not a band of light spreading out from the middle. A dot, small, sharp, localized, sitting at one specific place on the screen and nowhere else. If you had to describe what you just saw to someone who knew nothing about physics, you would say a tiny thing hit the wall and left a mark. The second electron arrives, another dot somewhere else, apparently unrelated to the first. The third lands somewhere else again. By the time 20 electrons have made the trip, what you're looking at is a scatter. 20 marks distributed across the screen in a pattern that looks, honestly, like nothing at all. Like the first drops of rain on a dry sidewalk. There is no structure in it. There is no order you could point to. If someone showed you this screen and told you it was the outcome of the experiment that broke classical physics, you would think they were joking. You're standing in front of that screen now. The room is dark except for the faint glow of the readout and the small green indicator on the detector housing. You can hear the low hum of the vacuum pump, and if the electronics are set to make a sound, a soft click each time something lands. Click, a dot, silence, click, another dot, well away from the first. You wait. The intervals feel long. Between clicks, nothing is happening that you can see. The apparatus is empty, the screen is still, and somewhere inside that stillness a single electron is making a journey you have no access to whatsoever. Click. A third dot. You lean closer. You're looking for the pattern. You know the pattern is supposed to be there. It is on the cover of textbooks and on the whiteboard of every lecture hall where this gets taught. Alternating bands, bright and dark, the signature of interference, and it is not there. 20 dots, and then 40, and then 100, and the screen in front of you shows a mess. Whatever is going to happen has not happened yet, and the strange thing, the thing that takes a moment to settle, is that it is not going to happen on the screen at all. It is going to happen in the accumulation. Keep the experiment running. Come back in an hour or 4 or overnight. Now there are tens of thousands of dots on the screen, and something has changed. The dots are no longer evenly scattered. They have piled up in certain places and stayed away from others, and if you step back far enough, the piles and the gaps form a series of alternating bands, regions where enormous numbers of electrons landed, separated by regions where almost none did. That is the interference pattern. That is the image everybody knows. Here is what I want you to notice about it, because everything else in the next 2 hours depends on it. At no point in that experiment did anyone see a wave. Not once. Not for an instant. The screen never displayed a rippling, spread-out, continuous disturbance moving through space. There was no moment when something wave-like arrived, and then somehow tightened itself into a dot. Every single detection event, from the first to the 10,000th, was a small localized mark at one location. The wave is not in the data. The wave is in the shape of the pile. The bands are a statistical structure. They describe how the landing sites are distributed across many, many repetitions. To see them at all, you need thousands of separate journeys by thousands of separate electrons, each one of which produced exactly one dot in exactly one place. The wave is a description of the histogram. It is a curve fitted to a very large number of individual particle-like events. It was inferred, reconstructed, calculated. Nobody has ever looked at it directly, because there is nothing there to look at. Let me say that in the plainest way I can, because we are going to keep coming back to it. You never see the wave, you see dots. And now the second half of the experiment, which is where the trouble usually starts. Suppose you're not content to let the electron make its journey unobserved. Suppose you install a detector at the slits, something that tells you which of the two openings each electron passed through. You run the experiment again, one particle at a time, and this time you get an answer every time. This slit, that slit, this slit again. Definite, unambiguous, one opening per electron, no hedging. But when you look at the accumulated pattern on the far screen after all those runs, the bands are gone. What you get instead is essentially two piles, one behind each opening, which is exactly what you would expect if you were firing small pellets at a wall with two holes in it. The interference structure has vanished from the statistics, so the system behaves one way when you interrogate its position and produces a different statistical structure when you leave it alone. That contrast, that specific reproducible 100-and-more-year-old contrast, is the entire observational content behind the phrase everybody has heard. Wave-particle duality. Sometimes it acts like a particle, sometimes it acts like a wave, except that we just watch the experiment carefully from the first dot to the last. And I want to point at something that is easy to walk straight past. In everything we observed there was no wave, there were dots, and there was the shape they made. The word wave was not something we found in the room. It was something we brought into the room with us, from somewhere else entirely, and laid over the top of what we saw. So where did it come from? What is the thing that word is actually naming? Because if nobody has ever seen it, and no instrument has ever registered it, and the theory's own rules guarantee that every measurement you make will hand you back a localized dot instead, then whatever the wave is, it is not the sort of thing we usually mean when we say that something exists. Part 2, 2 words, 1 sound. I want to tell you about a confusion, and I want to be upfront that it is a confusion about language rather than about physics, which is the sort of thing that sounds trivial right up until you see how much damage it has done. In physics, the word wave is used for at least two objects that have almost nothing in common. They have different mathematical structures, they live in different spaces, they have different relationships to measurement. One of them is unambiguously a physical thing you can stand inside, and the other one is an abstract function that nobody has ever detected and that most physicists cannot agree on the nature of. English gave them the same name, and physics kept the name, and everybody has been paying for it ever since. The first kind of wave is the one you already understand, even if you have never taken a physics course. It is a disturbance travelling through something. A sound wave is a pattern of pressure moving through air. A water wave is a pattern of displacement moving across a surface. A wave on a guitar string is the string itself moving. And the grandest example of the family, light, is a disturbance in the electromagnetic field, propagating through ordinary three-dimensional space at a very specific speed. These waves are real in the most ordinary sense of the word. They carry energy. They arrive somewhere. You can measure their strength at a given place with an instrument and get a number with units attached. The second kind of wave is the Schrödinger wave function, and it is not that. It is not a disturbance in a medium, because there is no medium for it to disturb. It is not a pattern in ordinary space, because it does not live in ordinary space. As we will see, it lives in a mathematical arena whose size depends on how many particles you're describing, and which for anything larger than a single particle has more dimensions than you can picture, or draw or build a model of. Its values are not measurable strengths. They are complex numbers, the kind with an imaginary part, and the imaginary unit is not a shortcut that cancels out at the end of the calculation. It sits structurally inside the equation itself. And in the standard textbook account, when you measure the system, this second kind of wave does something that no field in the rest of physics has ever been observed to do. It collapses. Two objects, one word, and the word is the one that gets used in every documentary, every classroom analogy, every popular article, every conversation at a party where somebody says the thing about how everything is really just energy vibrating. Think about what that word does to a person's mental picture. When someone says, an electron is sometimes a wave and sometimes a particle, what does the listener imagine? They imagine something like a ripple, a spreading disturbance moving through the room, going through both openings at once the way a water wave would, meeting itself on the far side and then, at the moment of measurement, suddenly gathering itself into a point, like a puddle running uphill into a drop. That image is vivid. It is memorable. It is the reason a lot of people fell in love with physics, and it is a hybrid of two things that were never the same thing. It takes the tangible, spatial, energy-carrying quality of the first kind of wave, and it grafts on the collapse behavior of the second kind, and it presents the result as a description of what an electron is. Nobody built that picture out of malice. It is the natural thing to build if you have been handed a single word for two different objects. And I want to be careful here, because there is a version of this observation that is just pedantry, the kind of correction that makes a conversation worse and teaches nobody anything. That is not what this is. The reason this distinction matters is that essentially every strange, unsettling reality as an illusion claim you have ever heard about quantum mechanics traces back through this confusion. The idea that observation creates reality, the idea that consciousness makes the world solid, the idea that matter is really just waves of energy, and therefore your thoughts can reshape it. All of these borrow the physical solidity of the first kind of wave and attach it to the observer sensitivity of the second kind, and neither half survives being moved. So here is what we are actually going to do tonight, and I am going to tell you plainly so that you know where we are headed. We are going to take those two waves apart. We are going to build the first one properly, the real one, the one made of fields, the one you have been inside of, so that you know exactly what a physical wave looks like and what it does and does not do. Then we're going to trace the history, step by step, of how the second one came to be called by the same name, because that history is specific and datable, and it happened over the course of about 25 years by a series of entirely reasonable decisions. Then we're going to look very carefully at what the second object actually is, where it lives, what it is made of, why nobody has ever seen one. And then we're going to ask the question in the title, which is the question this whole video exists to answer. If the thing everybody calls the wave in quantum physics is not a wave in any ordinary sense, if it is not a disturbance, not in our space, not detectable, not made of anything, then is it real at all? And if it is not, what is actually there instead? What is doing the work? Because something is producing those bands on the screen, and if there is no wave in the room, the explanation has to come from somewhere. I am going to give you an answer to that, a specific one, from a specific line of current research, and it is a genuinely satisfying answer that does not require anyone to give up on the world being knowable. But I am not going to give it to you yet, because it will not mean anything until you have seen the problem properly. And you cannot see the problem properly until you have seen what a real wave looks like. The kind that has never in the history of physics done anything mysterious at all. So let us start there, not with the electron, with the light in the room you're sitting in. Part 3. The wave that is real. To understand what a field is, forget physics for a second and think about a weather map. Take a map of a country and write, at every point on it, the temperature at that point. Not a temperature for the country as a whole, a temperature for every single location, however finely you want to slice it. That collection of numbers, one at every point, is a field. It is not a thing sitting somewhere on the map. It is a value assigned everywhere. And if you watch that map over the course of a day, you will see the numbers change and you will see patterns move across it, and those moving patterns are what a wave in a field is. The electromagnetic field works the same way, except that instead of a single number at each point, you have two sets of three, an electric field with a strength and a direction, and a magnetic field with a strength and a direction, at every point in space, at every moment. That is the whole object. It is not made of smaller pieces. It is not sitting in some other substance. It is a property of space itself, and it is there right now, everywhere around you, including in the space between your eyes and this screen. James Clerk Maxwell put the mathematics of that field into its modern shape in the 1860s, publishing the crucial paper in 1865 and the full treatment in his treatise of 1873. What he found in his own equations is one of the loveliest results in the history of science, and it is worth sitting with for a moment. Maxwell's equations contain two numbers that had been measured in laboratories by people doing very unglamorous work with capacitors and coils. One of them describes how strongly electric fields form in empty space. The other describes how strongly magnetic fields form. Neither of them has anything obvious to do with light. Neither of them was measured by anybody thinking about light. But when Maxwell combined his equations, he found that the field could sustain a travelling disturbance, a ripple in which a changing electric field produces a magnetic field, which in changing produces an electric field, which keeps the whole thing going as it moves forward. And when he calculated how fast that disturbance would travel, the answer came out of those two laboratory numbers. It came out to be the speed of light. Maxwell understood immediately what he was looking at. Light was not a separate phenomenon that happened to travel fast. Light was this. Light was a self-sustaining ripple in the electromagnetic field, and the reason it moves at the speed it does is that the field's own properties set that speed. Every colour you have ever seen is a different frequency of the same disturbance. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. All one family, all the same object, differing only in how quickly they oscillate. Heinrich Hertz confirmed it experimentally in 1887, more than 20 years after Maxwell wrote it down, and 8 years after Maxwell had died of cancer at 48, never having seen his prediction tested. Hertz built a spark gap on one side of a room and a small loop of wire with a gap in it on the other, and when he fired the first, a tiny spark jumped in the second. Something had crossed the room. Nothing had touched it. When someone asked him what use it might have, Hertz reportedly said it had none. It was just an experiment that proved Maxwell right. There is a 100-year-old radio industry, a global mobile network, radar, satellite navigation, and every wireless device in your home built on the thing he thought was useless. Now here is why I want you to hold on to this kind of wave very firmly. These waves are physical in every ordinary sense. Step outside on a clear day and stand in the sunlight, and the warmth you feel on your face is energy that left the surface of the sun about 8 minutes and 20 seconds earlier, carried by exactly this kind of disturbance and deposited into your skin. That is not a metaphor, and it is not an inference from statistics. Energy arrived. You can measure how much. Put a solar panel in the same spot, and it will hand you the number in watts. You can point at where these waves are. You can shield against them. A metal box will keep radio waves out, which is why your phone loses signal in an elevator. You can focus them, reflect them, polarize them, count the energy they deliver. At any point in space you can put an instrument in and get a reading with units on it. Volts per meter for the electric field, Tesla for the magnetic field. Real numbers, real units, real quantities. And there is one more property of these waves that I want to plant now, gently, because it is going to become the sharpest tool in this entire video, and I would rather you had it in your hand early. Consider a magnetic resonance imaging machine. If you have ever had a scan, or sat in a waiting room while someone you love had one, you know roughly what it involves. You lie very still inside a tube for a long and noisy while. What is happening inside that tube is that you are lying in the middle of an extremely strong static magnetic field. Clinical machines typically run at 1.5 or 3 Tesla. Research machines built for human imaging have gone past 11. To put that in perspective, the Earth's own magnetic field, the one that moves a compass needle, is around 50 microtesla, so a standard clinical scanner is putting you inside a field roughly 30 to 60,000 times stronger than the planet's. And while you are in there, the machine beam's radio frequency waves through your body and listens for what comes back. You are, in the most literal possible sense, lying inside a wave, several of them, and nothing happens to it. Nobody in the history of magnetic resonance imaging has ever had to worry that performing the wrong measurement might cause the magnetic field in the machine to collapse. It is not a concern. It is not on any checklist. The field does not care whether the technician is watching the readout, whether the patient is asleep, whether anyone in the building is conscious at all. Tens of millions of scans are performed worldwide every year, and the field simply sits there being a field, and the waves simply pass through and keep going. Say it plainly, nobody has ever collapsed a magnetic field. That sounds like an odd thing to bother saying. Of course nobody has. Why would they? Fields do not do that. That is exactly the point, and I want you to file it somewhere you can find it again, because in about an hour we are going to put that sentence next to a claim about the other kind of wave, and the two of them together are going to tell us something quite specific about what sort of object we're dealing with. For now, let this be the reference standard. This is what a wave looks like when it is real. It lives in the 3 dimensions you live in. It carries energy you can absorb. It has measurable strength at every point. It responds to nothing but the equations that govern it. Nothing about it is mysterious, and nothing about it has ever been mysterious in the 160 years since Maxwell wrote the equations down. Hold that. Because the next thing that happened in this story is that physics discovered light also comes in lumps. And for a while, that really was a paradox about a real wave. Part 4. The lump in the light. The trouble began, as trouble in physics often does, with an object glowing in a furnace. By the end of the 1800s, physicists had a problem they could not shake. Heat something up, a poker, a kiln, a star, and it glows, and the colour of the glow depends on the temperature. Cooler objects glow red. Hotter ones go orange, then white, then blue-white. This is completely familiar. It is also completely quantifiable, and by the 1890s there were good measurements of exactly how much light of each colour came out of a hot object at each temperature. The theory could not reproduce those measurements. Classical physics, applied honestly to the problem, predicted that a hot object should pour out more and more energy at shorter and shorter wavelengths, without limit. Open your oven door, and you should be sterilized by a burst of ultraviolet. This obviously does not happen, and the fact that the best physics of the era predicted that it should was not a minor discrepancy. It was a signal that something structural was wrong. That failure later acquired a name, the ultraviolet catastrophe, coined by Paul Ehrenfest in 1911, more than a decade after the problem had already been solved, which tells you something about how physics tidies up its own history. At the time, it had no dramatic label. It was simply a curve that would not fit, sitting in the middle of a subject that most senior physicists of the 1890s believed was essentially finished. There is a famous piece of folklore that a distinguished lecturer told a young Max Planck not to go into physics because there was nothing important left to discover in it. Whether or not the conversation happened exactly that way, the sentiment was widespread, and the man it was supposedly aimed at is the one who took the whole edifice apart. On the 14th of December, 1900, Max Planck presented a solution to the German Physical Society in Berlin, and he presented it apologetically. He had found that if you assume the oscillators in the walls of a hot cavity can only emit and absorb energy in discrete packets, not in a continuous flow, but in indivisible steps, each step proportional to the frequency of the light, then the mathematics produces exactly the observed curve, perfectly, every temperature, every wavelength. The size of the step is set by a constant, now called Planck's constant, and its value is about 6.626 times 10 to the minus 34th joule seconds. That is an absurdly small number, and it is worth trying to feel how small. If you wanted to scale that number up to the number 1, to make the quantum of action an everyday-sized quantity, you would have to inflate everything else by the same factor, and a single grain of sand would end up more massive than everything in the observable universe. That is how far below ordinary experience the graininess of the world sits. It is why nobody noticed it for 250 years of doing physics. Planck himself did not believe he had discovered anything about the nature of light. He thought he had found a mathematical trick, a bookkeeping constraint on how the walls of the cavity behaved, which would eventually be explained away by some more sensible derivation. He described it later as an act of desperation. He spent years trying to get rid of it. It was Albert Einstein who took the packet seriously, in 1905, in one of 4 papers he published that year that between them rearranged physics. The paper on light quanta was the one he himself described as revolutionary, and it addressed a phenomenon called the photoelectric effect. Shine light on a metal surface, and, under the right conditions, electrons come flying off. The details of that effect were maddening for anyone who thought of a light purely as a Maxwell wave. If light is a continuous wave, then brightness is energy, and a brighter light should knock electrons off with more energy. It does not. Turn the brightness up and you get more electrons, each one with exactly the same energy as before. What changes the energy of the ejected electrons is not the brightness but the colour, the frequency, and below a certain frequency nothing comes off at all, no matter how bright you make the light, no matter how long you leave it on. Einstein's explanation was that light delivers its energy in discrete lumps, each carrying an amount of energy set by its frequency and by Planck's constant. One lump knocks out one electron. A brighter beam is a beam with more lumps in it, so it knocks out more electrons, each with the same energy as before, and if the individual lump does not carry enough energy to break an electron free of the metal, then no amount of piling up more lumps will do it, which is exactly the threshold behaviour that had been observed. This was so hard to swallow that Robert Millikan spent roughly a decade doing careful experiments explicitly designed to disprove it, and ended up confirming it to high precision and remained unhappy about it for years afterward. Einstein's Nobel Prize, awarded in 1922 for the year 1921, was for this work. Not for special relativity, not for general relativity, for the light quantum, for the idea that everyone, including the Nobel Committee, still found uncomfortable. It is worth pausing on how thoroughly that uncomfortable idea has since embedded itself in ordinary life. Every solar panel on every roof works by the photoelectric effect. A lump of light arrives, a lump of light frees a charge carrier, and the accumulated freeing of charge carriers becomes a current you can run a house on. Every digital camera sensor works the same way, counting arrivals of light quanta well by well and turning the count into a brightness value. The photomultiplier tubes that detect faint astronomical signals and the sensors that see you approaching an automatic door are the same physics. Einstein's revolutionary paper is now, 120 years later, in the specification sheet of devices sold at hardware stores. That is the usual fate of a good idea in physics. First it is unbelievable, then it is controversial, then it is infrastructure. The word photon did not arrive until 1926, coined by the American chemist Gilbert Lewis, in a paper whose actual central thesis was wrong. The word stuck anyway. The name for the most important particle in the history of the subject came from a paper nobody remembers the argument of. Now, here is the part I want to be very precise about, because this is the hinge of the whole video. There was now a genuine paradox about light, and it was a paradox between two real things. On one side you had Maxwell's electromagnetic wave, a real disturbance in a real field, spread out through three-dimensional space, which explained interference and diffraction, and polarization and refraction, and about a century of optics with total success. On the other side you had the light quantum, a discrete localized delivery of energy, which explained the blackbody curve and the photoelectric effect, and would go on to explain a great deal else. Both descriptions worked, both were supported by experiment, and they seemed to be describing incompatible kinds of object. This was the original wave-particle duality, and I want to stress that the tension was real, and the word wave in it meant something completely definite. It meant Maxwell's wave, the three-dimensional, energy-carrying, measurable at every point, never collapsing kind we spent the last section building. That tension eventually got resolved, and the resolution is worth knowing because it is genuinely clean. Quantum field theory says the electromagnetic field is the fundamental object. It fills space, and a photon is a discrete excitation of it, the smallest possible packet of disturbance that the field can carry at a given frequency. The field is the wave. The photon is a unit of the field's excitation. There is no contradiction because they are not two competing objects. One is the thing and the other is a quantized amount of the thing. That resolution took a few more decades and a great deal of mathematics, but it exists and it works. So for light, the story has an ending. The phrase wave-particle duality was coined to describe a real conflict between two real descriptions of a real field, and quantum field theory dissolved the conflict by explaining how both descriptions could be true at once. Everything I have just said is defensible, historically accurate, and reasonably well known. And then the same phrase, the same three words carrying all of that hard-won meaning, got applied to the electron, to matter. And the wave in the phrase quietly changed into something else entirely, and almost nobody noticed, because the word did not change at all. Part 5. The equation that worked too well. Louis de Broglie was a French aristocrat who came to physics through history. He took a degree in history first, and turned to theoretical physics partly under the influence of his older brother Maurice, who ran a private laboratory in the family mansion in Paris. In 1924, he submitted a doctoral thesis containing an idea so simple you can state it in one sentence, and so consequential that it took a generation to work out. His reasoning went like this. Light had been understood as a wave, and had turned out to also come in particle-like lumps. Perhaps the symmetry runs both ways. Perhaps things that had always been understood as particles, electrons for instance, also have a wavelength associated with them, and he wrote down what that wavelength should be. Planck's constant divided by the particle's momentum. Faster and heavier means shorter wavelength. Slower and lighter means longer. It is worth putting a number on that formula, because the number explains why nobody had noticed. Take an electron in a typical laboratory beam, and its de Broglie wavelength comes out around 1/10 of a nanometer, roughly the size of an atom, which is precisely why it diffracts off the regular spacing of a crystal. Now take a baseball thrown at 90 miles an hour. Its wavelength works out to something like 10 to the minus 34th of a meter. For comparison, a proton is about 10 to the minus 15th of a meter across, so the baseball's wavelength is smaller than a proton by a factor of a billion. There is no aperture in the universe narrow enough to diffract it. Matter waves are not absent from everyday life because everyday objects are exempt from the rules. They are absent because the effect is scaled down past every possible means of noticing. The examining committee at the Sorbonne did not know what to make of it. The story is that they forwarded the thesis to Einstein for an opinion, and Einstein wrote back that de Broglie had lifted a corner of the Great Veil. He passed. The prediction was tested in 1927, and it was tested twice, independently, on 2 continents. Clinton Davison and Lester Germer at Bell Telephone Laboratories in New Jersey were firing electrons at a nickel target, a fairly routine surface physics experiment. When a bottle of liquid air broke, air rushed into their vacuum chamber and the nickel oxidized. To repair it, they heated the nickel hard, which recrystallized it into large crystal grains. When they resumed the experiment, the electrons scattered off the newly regular crystal in a pattern of sharp peaks and troughs at exactly the angle de Broglie's formula predicted. An accident with a broken bottle produced one of the most important results of the decade. In the same year, George Paget Thompson in Aberdeen fired electrons through thin metal foils and got diffraction rings. There is a detail here that people who like irony enjoy. George Paget Thompson's father was Joseph John Thomson, who had discovered the electron in 1897 and won a Nobel Prize for demonstrating that it was a particle. His son won a Nobel Prize for demonstrating that it diffracts. Both were right. Neither of them was wrong. That is how strange this subject is. So by 1927, matter diffracts. That is a hard experimental fact, and it has never gone away. What was still missing was an equation, something that would let you actually calculate for a given system what would happen. Erwin Schrödinger supplied it in 1926, in a burst of productivity that is genuinely difficult to comprehend. 4 papers, all under the title Quantization as an Eigenvalue Problem, published in the Annalen der Physik across a single year. Between them they laid down the equation that still bears his name, and that every physics student on Earth still learns. He was not the only person to have solved the problem, which is part of why the interpretive question got shelved so quickly. A year earlier, in 1925, Werner Heisenberg had produced a completely different formulation, matrix mechanics, built out of arrays of numbers representing observable quantities, with no picture of anything moving through space and no intention of providing one. The 2 approaches looked nothing alike. They used different mathematics, rested on different instincts, and were championed by people who did not much care for each other's methods. Schrödinger wrote that he was repelled by matrix mechanics, and Heisenberg wrote privately that he found Schrödinger's picture disgusting. Within months it was shown that the 2 formalisms are mathematically equivalent. They are the same theory in different clothing. That was a triumph for the mathematics and, in a quiet way, a defeat for interpretation, because it demonstrated that you could get every correct answer without ever settling what the theory was about. What made it overwhelming was not the philosophy. It was that it worked, immediately, on the problem everyone cared about. The hydrogen atom had been described a decade earlier by Niels Bohr with a set of rules that were frankly arbitrary. Electrons occupy certain orbits and not others, and here are the allowed orbits, and please do not ask why. Schrödinger's equation did not need those rules. You wrote down the equation for an electron near a proton. You demanded that the solution be well-behaved everywhere, not blowing up, not multiple-valued, just mathematically sensible. and the allowed energy levels fell out on their own. The quantization was not imposed. It emerged, the same way the allowed frequencies of a guitar string emerge from the fact that the string is tied down at both ends. That is a beautiful result, and it deserved every bit of the excitement it caused. It also created the problem this entire video is about, because it left one question conspicuously open. The equation describes the evolution of a thing usually written with the Greek letter psi. Everyone could calculate with psi. Nobody knew what psi was. Schrödinger had a proposal, and it is important because it was the reasonable one. He thought psi described a real physical density spread through space, that the electron was not a point at all but a smeared cloud of charge, and that the wave was that cloud. That is a picture. It is intelligible. It puts something real in the room. It did not survive. The problem is that solutions to his equation spread out over time. A wave packet that starts narrow gets wider and wider as it evolves. That is generic behavior for this kind of equation. So if the electron really were a spreading cloud of charge, a free electron would smear itself across a room in a fraction of a second and stay smeared. And that is not what we find. We find, every single time, a compact localized landing. We find a dot. Whatever spreads out in the equation, it is not the electron's charge, because the electron's charge arrives all in one place. Max Born supplied the interpretation that stuck, also in 1926, and there is a detail about how he did it that says a great deal. In the paper where the probability idea first appears, the crucial statement that what you square to get a probability is psi itself was strengthened in a note added while the paper was in proof. The single most consequential interpretive move in the history of quantum mechanics arrived partly as a correction inserted at the last minute. It took 28 years for it to be recognized with a Nobel Prize in 1954. Born's answer was that psi is not a substance. It is an amplitude, and the square of its magnitude gives you the probability of finding the particle at a given place. The wave is not the electron. The wave is a distribution of chances. Schrödinger hated it. That is not a dramatization. He said so in print and in letters, repeatedly, for decades. He had built the equation hoping to restore something like a continuous, visualizable physical picture to atomic physics, to get away from what he saw as the arbitrariness of the Bohr rules and the abstraction of Heisenberg's matrix methods. What his own mathematics handed back to him was an abstract complex valued function whose only connection to the world was through a rule for generating probabilities. He's famous now, partly for a thought experiment about a cat that he invented specifically to show how absurd he thought the standard interpretation was. It is one of the great ironies of the subject that his attempted reductio is now the single most popular illustration of the thing he was mocking. I want to sit here for a moment, because there is something genuinely sad in it that is easy to skip past. Erwin Schrödinger built the most useful equation in 20th century physics. It underwrites chemistry. It underwrites the transistor. It is the working tool of every material scientist, every quantum chemist, every semiconductor engineer alive, and he spent much of the rest of his life unable to believe in the central object it describes. He wanted a wave, a real one, in real space, made of something, the kind we spent the last section building. What he got was a function on a space that does not exist, which tells you the odds. The man who put the word wave on this object may have been the first person to suspect that it was not one, and that is the moment, right there, in 1926. That is where the two waves got the same name, because de Broglie's original guess really did sound like the first kind of wave, a wavelength associated with a particle, a ripple, in space, of the sort you could imagine. That is what everybody heard, and that is what got taught, and that is the image that ended up in every popular account for the next 100 years. But the object that actually appears in Schrödinger's equation, the thing that does the calculating and makes the predictions, is not that. It is something else, and to see how much else, you have to ask a question that almost nobody asks, not what the wave is made of, where it lives. Part 6. The room with too many dimensions. Every wave in ordinary physics has an address. A sound wave is in the air of this room. An ocean swell is on the surface of the water. Light from your lamp is in the space between the bulb and your eyes. You can walk over and stand where the wave is. So, where is the Schrödinger wave function? The answer is that it lives in something called configuration space, and configuration space is not a place. It is a mathematical device for keeping track of arrangements, and the moment you understand how it is built, something about the standard story stops being available to you forever. Here is how it works. Suppose you have a system, and you want a single mathematical object that captures the entire arrangement of that system at one instant. Not one particle's position, the whole arrangement all at once. Configuration space is the space in which one single point represents one entire arrangement of the whole system. For a single particle, that is easy. To specify where one particle is, you need 3 numbers: how far along, how far across, how far up. So configuration space for one particle needs 3 axes, 3 dimensions. And this is the coincidence that has misled essentially everyone who has ever been taught this subject. Because a 3-dimensional configuration space looks exactly like the room you are sitting in. When you draw the wave function of a single electron, it looks like a shape in space, spreading out and moving around and passing through slits. It looks like a ripple. And so the natural conclusion is that it is a ripple in space, and that the wave in wave-particle duality means what it usually means. It does not. That resemblance is an artifact of arithmetic. One particle needs 3 numbers, ordinary space has 3 dimensions, and the 2 happen to match. The moment you add a second particle, the match is gone and it never comes back. Because now you need 6 numbers to specify the arrangement. 3 for the first particle, 3 for the second. So configuration space has 6 dimensions, and the wave function is a single object defined over all 6 of them at once. Not 2 waves, 1 for each particle, each rippling around in your room. One wave in a 6-dimensional space, whose value at a point depends on where both particles are simultaneously. You might reasonably ask why anyone would insist on that. Why not just use 2 ordinary waves in ordinary space, 1 per particle, and be done with it? The answer is that for most systems you cannot. It is mathematically impossible. There is a property called entanglement, and what entanglement means in this language is precisely that the wave function of a 2-particle system cannot be broken apart into a product of 2 separate 1-particle functions. It does not factor. There is no way to say, here is the first particle's wave, and here is the second particle's wave, because the object contains correlations between them that are not stored in either half. Ask it about particle 1 alone, and it will not answer. The information you want is only there in the relationship, and a mathematical object whose content is irreducibly about pairs cannot be redrawn as 2 objects sitting in a shared room. It requires the bigger space. That is not an aesthetic preference on anyone's part. It is why the 6 dimensions are not optional. Take a moment with that, because it is easy to nod past and it is the crux of everything. Imagine then trying to visit this space. You step through a door expecting a room. You're looking for the electron's wave, the ripple, the thing you have seen animated in 100 documentaries, and the room has 6 directions. Not 6 directions in the sense of north, south, east, west, up, down. Those are only 3 axes counted twice. 6 independent directions, each perpendicular to all the others, none of which you can point at. There is no wall you can walk toward. When you try to picture it, your mind produces a 3-dimensional room and quietly discards the rest, and you can feel it doing that, and you cannot stop it. And that room, the 6-dimensional one, is the small case. That is 2 particles. Now add the 98 others you would need for a small molecule. Now walk into the room belonging to a single speck of dust drifting through the light from a window. A speck containing something like 1 billion atoms, needing something like 10 billion directions to describe. There is no walking into it. There is no picturing it. There is not even a failed picture. There is just the arithmetic running out ahead of you into a size that has no image at all. Let me put actual numbers on it, because the numbers do work that adjectives cannot. A hydrogen molecule, the simplest molecule there is, 2 protons and 2 electrons, has a configuration space of 12 dimensions. Its wave function is a complex valued function of 12 position variables plus time. There is no picture of it. There has never been a picture of it. Every image you have ever seen of a molecular orbital is a projection, a slice, a summary, a shadow of a 12-dimensional object cast onto 3 dimensions so that a human can look at it. A single grain of dust contains roughly 10 to the 18th atoms. Its configuration space has on the order of 10 to the 19th dimensions. For scale, the number of stars in the observable universe is estimated at something like 10 to the 22. So the number of dimensions in the wave function of one dust mote is within a few factors of 1,000 of the number of stars in everything we can see. One speck. Off your bookshelf. A mole of any substance, 18 grams of water, about a tablespoon, contains 6.02 times 10 to the 23rd particles. Its configuration space has more dimensions than there are grains of sand on Earth, more than there are atoms in 10,000 planets, and that is a tablespoon. If the wave function is a physical object, then that is the arena the world actually happens in. The 3 dimensions you move through would be a kind of derived appearance, a low-resolution shadow of a fundamental space that grows every time a particle is added. Some very serious physicists accept exactly that. It is not a foolish position, and I am not going to caricature it. But I want to be clear about what accepting it costs, because it is usually presented as though the only strange thing about quantum mechanics is the randomness. People noticed the cost immediately, by the way. At the 5th Solvay conference in Brussels in October of 1927, the conference that produced the most famous photograph in physics, 29 people in the frame, 17 of whom would end up with Nobel Prizes, Einstein raised an objection that is still, a century later, one of the sharpest things anyone has said about this. Consider a single particle heading toward a screen, he said, with its waves spread out over the whole surface. The particle lands at one spot. In that instant, the possibility of it landing anywhere else has to vanish, everywhere on the screen at once, no matter how far apart the two ends of the screen are. If that spread out thing is physically real, then something just happened instantaneously across a distance, and relativity says nothing happens instantaneously across a distance. Hendrik Lorentz chairing could not resolve it. Nobody in the room could. The objection was not answered so much as set aside, and the field moved on to calculating because the calculating was going extremely well. There is one more structural oddity worth noticing while we are here. If you look at the shape of the Schrödinger equation, first order in time, second order in space, it is not the shape of a wave equation at all. The equation that describes sound, or light, or a vibrating string is second order in time. Schrödinger's is not. Its actual mathematical relative is the diffusion equation, the one that describes heat spreading through metal, or a drop of ink spreading through water. It is a diffusion equation with an imaginary coefficient stuck in front. So even at the level of its bones, the thing we call a wave is closer to a spreading of probability than to a ripple, and the dimensions are not even the whole of it. There are 2 more properties of this object that no field in the rest of physics has. The first is that its values are complex numbers. When you measure an electric field at a point, you get a number with units, so many volts per meter, and it is a real, ordinary number of the kind you can mark on a ruler. The wave function's value at a point is not like that. It is a complex number. It has a real part and an imaginary part, built on the square root of -1. And this is not a calculational convenience that washes out at the end. The imaginary unit sits inside the Schrödinger equation itself, structurally, as part of how the thing evolves in time. You cannot rewrite the theory to remove it without breaking it. Whatever the wave function is, it is not measured in any units that exist, because half of it is a number that does not appear on any instrument ever built. The second is normalization. The wave function is required, by the theory, to have its total squared magnitude add up to exactly 1. That is a rule, imposed from outside, and it is imposed for a completely transparent reason, because the total probability of finding the particle somewhere has to be 100%. If you ask why a field would be required to sum to a fixed number, there is no physical answer, because that is not the kind of constraint physical fields are subject to. The electromagnetic field is under no obligation to integrate to anything in particular. It is what it is. But a probability distribution has to sum to 1, because that is what it means to be a probability distribution. That constraint is a fingerprint. It is the sort of condition you impose on a ledger, not on a substance. So let us take stock of what this object is, described plainly and without loading the description. It lives in a space that has more dimensions than there are stars, and the number changes depending on how many particles you decide to include in the system. It takes values that are partly imaginary. It is required to sum to 1. It has never been detected by any instrument, and every prediction it makes is a probability that something localized and particle-like will show up at a particular place. I'm going to call that space the room with too many dimensions, and we will be coming back to it, because later tonight we're going to find a room that is very much larger. And there is still one more thing this object does that no field has ever done. We have been circling it since the beginning. It is the strangest item on the list. It is the one that made this whole subject sound like philosophy, and it is the single most useful clue we have. It collapses. Part 7. Let's put the pieces together. Before we go further, let us step back and stack up what we have, slowly, in plain language. We're about halfway through, and this is a good place to put the pieces side by side. We started in a dark room with an experiment running one electron at a time, and we established the plainest fact in this entire subject. The screen shows dots. It has only ever shown dots. Every detection event, from the first experiments with faint light in 1909 to the modern versions using molecules of 2,000 atoms, is a small localized arrival at one place. The banded interference pattern is a shape made out of thousands of those arrivals piled up. It is a histogram. Nobody has ever observed a wave in that apparatus, and the theory's own rules guarantee that nobody ever will, because the only bridge from the mathematics to the world converts the wave into odds for exactly the kind of localized landing that looks like a particle. Then we built the first kind of wave properly. A field is a set of values at every point of ordinary space. A wave in a field is a pattern moving through those values. Light is one, a self-sustaining disturbance in the electromagnetic field, travelling at a speed that falls out of two laboratory constants, carrying energy that warms your face, measurable at any point with an instrument that hands you a number with units on it. You have been inside these waves. You're inside several right now. They are as real as anything in physics gets. Then we followed the history. Planck in 1900 and Einstein in 1905 found that light also arrives in discrete lumps, and that produced a genuine paradox. But a paradox between two real things, resolved eventually by quantum field theory, which says the field is the wave and the photon is a unit of its excitation. That was the original wave-particle duality, and the word wave in it meant Maxwell's wave, and it meant it exactly. Then, in 1924 and 1926, the phrase got applied to matter. De Broglie guessed that particles have wavelengths. Schrödinger wrote the equation. Born supplied the interpretation, and the object that came out the other end was not a disturbance in a field. It lives in configuration space, which for anything beyond a single particle has more dimensions than a person can picture. Its values are complex numbers. It is required to sum to 1. It does not factor when particles are entangled, which is why the extra dimensions are not a choice, and it has never registered on any instrument in 100 years of trying. So we now have 3 separate objects on the table, and one word doing duty for 2 of them. There is the particle, the thing that lands, the thing that makes the dot. There is the field wave, real, 3-dimensional, energetic, measurable. And there is the wave function, abstract, high-dimensional, complex, normalized, undetected. Popular science calls the second and third of those by the same name, and the result is the mental image almost everyone carries, a ripple in the room that suddenly gathers itself into a point. That is where we are. And I have deliberately left one thing on the table, because it is the sharpest thing we have, and I wanted you to have everything else in place before we picked it up. Of those 3 objects, exactly one of them does something when you look at it. The particle does not change because you observed it. It lands where it lands. The electromagnetic field does not change because you observed it. You can lie inside one for 40 minutes in a hospital tube while a machine beams waves through your chest, and nothing anyone measures makes that field jump discontinuously into a different configuration. But the wave function in the standard textbook account does exactly that. You measure, and it collapses, instantly, everywhere, into something entirely different from what it was a moment before. One of these 3 is behaving differently from the other 2, and when one item on a list behaves unlike everything else on the list, that is usually not a mystery to be deepened. That is a clue about which category it belongs to. It is the one loose thread we have not pulled, and it turns out to be attached to everything else. Let us go and look at the collapse properly. Part 8. Nobody has ever collapsed a magnetic field. There is a peculiar thing about the structure of quantum mechanics that students notice in their first serious course and then are quietly trained to stop noticing. The theory has 2 rules for how things change in time, and the 2 rules have nothing to do with each other. The first rule is the Schrödinger equation. It is smooth, continuous, entirely deterministic, and completely reversible. Run it backward and you recover exactly where you started. Given the wave function now, it tells you the wave function at any other time forever, with no randomness anywhere in it. It is, in that respect, as well behaved as Newton's laws. The second rule is measurement. When you measure, the wave function does not evolve smoothly. it jumps. Whatever spread out structure it had is discarded, and it becomes, abruptly, the specific state corresponding to the result you got. This jump is discontinuous, irreversible, and random. You cannot predict which outcome you will get, only the odds. And those odds come from the Born rule. The probability of a given result is the squared magnitude of the wave function's value there. I want to point at something about that squaring operation, because it is quietly informative. The wave function's values are complex numbers, and a complex number carries two pieces of information, a magnitude and a phase. When you take the squared magnitude to get a probability, you throw the phase away. It is discarded entirely. So the theory's own bridge to observation systematically destroys half the information in the object it is bridging from. Whatever the wave function is, it carries more structure than any single measurement can ever reveal, and the structure it carries in excess is precisely the part that produces interference. Now the deeper problem, and the one that has generated a century of literature. The second rule cannot be derived from the first. This is not a matter of nobody having tried hard enough. The Schrödinger equation is smooth, deterministic, and reversible. Collapse is abrupt, random, and irreversible. You cannot get the second out of the first, because the first has none of those properties in it. So the standard formulation of quantum mechanics contains two separate dynamical laws, one of which applies when nobody's looking, and the other of which applies when somebody is, and the theory does not tell you where the boundary between those situations is. John von Neumann set this out with total clarity in his book on the mathematical foundations of quantum mechanics, published in 1932, more than 90 years ago. He labelled the two kinds of evolution as separate processes and showed that the boundary between them can be slid up and down the chain from the particle to the apparatus to the observer's eye to the observer's brain, and that the theory's predictions do not change no matter where you put it. That flexibility sounds like a virtue. It is actually a symptom. A physical theory should not be indifferent to where its most dramatic event happens. This is the measurement problem. It is the single most persistent unsolved question in the foundations of physics. It is older than nearly everyone alive, and it exists in this form only if you assume the wave function is a physical object that has to physically do something when a measurement occurs. So let me put the sentence I asked you to hold on to next to it. Nobody has ever collapsed a magnetic field. I want to make that as concrete as I can, because concreteness is the whole point of it. Somewhere tonight, in a hospital, someone is lying inside a magnetic resonance scanner. Perhaps you have been that person. Perhaps you have been the one sitting outside watching a clock holding somebody's coat. If so, you know the texture of it. The flat table, the padding, the instruction to hold very still, the extraordinary noise, the banging and buzzing that comes from the gradient coils physically flexing as the current in them switches. Here is what is happening to you in there. You are lying at the center of a superconducting magnet producing a static field of 1.5 or 3 Tesla. The Earth's own magnetic field, the one that turns a compass, is around 50 microtesla. So you are inside a field roughly 30 to 60,000 times stronger than the planet's. And through that field, the machine is beaming radio frequency waves, real electromagnetic waves of the kind we built in Part 3, into your body, and listening for the faint signal that comes back from the hydrogen nuclei in your tissue. You're lying inside a wave, you're lying inside several, and in the entire history of this technology, tens of millions of scans a year, across decades, in every country with a hospital, nobody has ever had to worry that performing the wrong measurement might cause that field to collapse. It is not on any safety checklist. It is not a failure mode. It is not a thing that engineers design around, because it is not a thing. The field does not care whether the technician is watching the console, whether the patient is asleep in the tube, whether anyone in the building is conscious. The radio frequency waves are not in a superposition of having been emitted. The magnet does not require an observer. And I want to let that sit for a second, because there is something in it that goes past the argument. You have been inside one of these waves, physically, bodily, for 40 uncomfortable minutes, or standing in the sun this afternoon, or right now with the light from this screen landing on your face. That is one of the two things physics calls a wave, and you have direct personal acquaintance with it. The other one, you have never been inside. Neither has anyone. There is no possible experience of being inside a wave function, no instrument that has ever registered one, no unit it is measured in, no place it can be said to be. And that object, the one nobody has ever encountered, is the one that supposedly cannot survive being looked at. Someone is going to say, but decoherence solved this. It is worth answering, because decoherence is real and important, and it does not do what it is often said to do. Starting with Heinz-Dieter Zeh in 1970, and developed considerably by Wojciech Zurek through the 1980s, decoherence theory shows that a quantum system interacting with a large environment loses its capacity to show interference extremely quickly. For a dust grain in ordinary air, the timescale is something like 10 to the minus 31 seconds, which is effectively instant. That explains beautifully why you never see a chair in two places. What it does not do is produce one outcome. Decoherence turns a superposition into something that looks statistically like a list of possibilities with weights attached. It does not pick an entry off the list. The question of why you got this result and not that one survives it entirely. Now, I want to be careful here, because this is a clue and not yet a proof, and I would rather be honest with you than tidy. You could accept everything I have just said and still hold that the wave function is physically real. Plenty of thoughtful physicists do. You would then say that collapse is a real physical process, genuinely different from anything else in nature, and that our job is to work out its mechanism, and there are serious research programs doing exactly that, which we will get to. That position is available and it is not silly. But there is a much more ordinary way to read the asymmetry, and it is the reading that makes the strangeness evaporate. Think about a card, face down on a table. Before you turn it over, your description of it is a probability distribution, 1 chance in 52 for each possibility. You turn it over. It is the 7 of clubs, and in that instant your probability distribution collapses. The other 51 possibilities go to 0, immediately, completely, and, if you like, faster than light, because there is no signal involved. Nothing physical happened to the card. The card was the 7 of clubs the whole time. What collapsed was a ledger, and ledgers are allowed to change discontinuously when you learn something, because that is what learning is. If the wave function is a ledger rather than a substance, then collapse is not a physical event demanding a mechanism. It is an update. The measurement problem in that reading is not solved so much as dissolved. It was a problem about the physics of an object that was never doing physics in the first place. That is a large claim, and I have not earned it yet. Because before we can say the wave function is bookkeeping, we have to deal with an inconvenient fact that I have been holding back. The electron does have a real field, a genuine one, in genuine three-dimensional space, part of the standard model of particle physics, and it is not the wave function. Part 9. The electron really does have a field. Here is the fact that makes this whole subject genuinely difficult rather than merely badly explained, and I want to give it its full weight rather than tiptoe around it. Modern fundamental physics is not a theory of particles, it is a theory of fields. The standard model, the framework that describes every known particle, and 3 of the 4 forces, tested to more decimal places than any other theory ever constructed, is a quantum field theory. In it, there is no such thing as an electron sitting somewhere as a fundamental object. There is an electron field, defined at every point of ordinary space, in the same way the electromagnetic field is defined at every point of ordinary space. An electron is an excitation of that field, a localized packet of the field being disturbed. The field is fundamental. The particle is what a unit of disturbance in it looks like. The electron's field is called the Dirac field, after the equation Paul Dirac wrote in 1928, and the story of that equation deserves 30 seconds because it is one of the boldest things in the history of physics. Dirac wanted an equation for the electron that was consistent with special relativity, which Schrödinger's was not. He found one. It worked, and it explained the electron's magnetic properties without anyone having to put them in by hand. But it also had solutions with negative energy, which appeared to be nonsense, and Dirac spent years trying to make them mean something acceptable. At one point suggesting they might be protons, which does not work at all, since protons are nearly 2,000 times heavier. Eventually he accepted what the mathematics was saying. There must exist a particle with the electron's mass and the opposite charge. Nothing of the kind had ever been observed. In 1932, Carl Anderson found exactly such a track in a cloud chamber photograph of cosmic rays and named the particle the positron. He was 31 when he won the Nobel Prize for it. An equation had predicted a whole category of matter before anyone had seen a scrap of it. So the electron has a field, a real one, in 3 dimensions, part of the best tested theory in science. And that field is not the Schrödinger wave function for an electron. I want to say that slowly, because it is the single most conflated pair of objects in popular physics. The Dirac field is defined on ordinary spacetime, 3 dimensions of space and 1 of time, and it is there whether or not you are studying any particular electron. The wave function is defined on configuration space, whose dimensionality depends on how many particles you have decided to include in your system, and it is a probability amplitude, not a disturbance in anything. They have different domains, they have different mathematical types, they play different roles. One is a piece of the furniture of the world, the other is a device for calculating odds. So for the electron, we now have 3 separate things in play, and you will find all 3 of them called the electron's wave, somewhere on the internet tonight. There is the particle, the thing that lands and makes the dot. There is the Dirac field, the physical field in ordinary space, of which the electron is an excitation, and there is the wave function, the abstract high-dimensional bookkeeping object. 3 objects. 2 of them share a word they should not share, and the third gets dragged in because it is the only one anybody can picture. And now it gets stranger, in a way that matters enormously for where this video is going. The Dirac field is not a classical field in the way the electromagnetic field is. You cannot picture it the way you can picture magnetic field lines curving around a bar magnet, and this is not a failure of imagination. Electrons belong to a family called fermions, particles with intrinsic angular momentum of 1/2 in the units physics uses. Quarks are fermions. Protons and neutrons, built from quarks, behave as fermions. Essentially everything you would call matter is made of them. Fermions obey a rule that Wolfgang Pauli formulated in 1925. No 2 identical fermions can occupy the same quantum state. This is the exclusion principle, and mathematically it forces the field-theoretic objects describing fermions to be built from quantities that anti-commute, quantities where swapping the order of 2 of them flips the sign of the result. There is no everyday number that behaves that way. There is no classical field configuration you can draw. The mathematical machinery required has no picture attached to it at all, which is why popular explanations tend to skip straight past the Dirac field and go back to talking about ripples. Pauli's rule sounds like an abstraction about states and quantum numbers. Let me show you where it is right now. Put your hand flat on the nearest solid surface. A table, a desk, the arm of a chair. Press down. Something is stopping you. Go looking for what it is. Down past the grain and the finish, into the cellulose fibers, into the molecules, into the individual atoms. And here is the thing about an atom. It is overwhelmingly empty. If the nucleus were the size of a marble in the middle of a football stadium, the electrons would be somewhere out past the seats. There is nothing solid down there. There is essentially nothing down there at all. What stops your hand is not stuff meeting stuff. The electrons in your skin and the electrons in the table repel each other electrically. Yes, but the deeper reason the table cannot be compressed, the reason its atoms have any size in the first place, is exclusion. The electrons in each atom cannot all fall into the lowest energy state, because they are fermions and only so many can occupy each state. So they stack upward into shells. The stacking is what gives an atom volume. The volume is what makes matter take up room. That pressure in your palm is a rule about half-integer spin, made physical. Widen out from your hand. That same rule builds the periodic table. The shell structure is why the elements repeat their chemical behavior in the pattern they do, why sodium is violent and neon is inert, why carbon can build the chemistry you're made of. Without exclusion there is no chemistry, because every electron in every atom would sit in the ground state, and nothing would ever bond to anything. Widen out further. When a star like the Sun exhausts its fuel and its core collapses, what eventually halts the collapse is electron degeneracy pressure, exclusion, operating on a stellar scale, refusing to let the electrons be pushed into the same states. That is what a white dwarf is, a sun's worth of matter held up against its own gravity by the same principle that is currently holding your palm off the table. A teaspoon of it would weigh several tons, and it works up to a limit, calculated by Subramanian Chandrasekhar as a young man on a boat to England, of about 1.4 times the mass of the Sun. Above that, gravity wins, and the exclusion fails and the star keeps going. To a neutron star, where the same principle applies to neutrons at densities where a sugar cube of the material would weigh about as much as all of humanity, or past that, to a black hole. Your hand, the periodic table, and the existence of white dwarf stars are all the same rule. and that rule is a fact about the fermion fields, the real ones, in real space. It is not a fact about the wave function, the thing that makes matter solid, and the thing that popular science tells you your electrons really are two entirely different objects. There is a mirror image family too, which makes the contrast sharper. Particles with whole number spin are called bosons, and they obey the opposite rule. They are perfectly happy to pile into the same state, without limit. Photons are bosons. That is exactly why a laser works. You can persuade trillions of photons into one identical state, and they will go cheerfully, which is something no electron would ever do. So the same underlying property, the spin, decides whether a thing can be stacked or must be stacked apart, and that single fork in the road is the difference between light and matter, so nobody should feel foolish about being confused here. The confusion is not personal, it is structural, it is built into the vocabulary, and it has been sitting there for a century. Which raises an obvious question. What if we have this backwards? What if the wave function really is physically real, and we have simply been too squeamish to accept the consequences? There is a version of quantum mechanics that says exactly that, and it is the most serious rival on the table. It has been worked out in enormous detail by very good people, and what it costs to build is the clearest measure we have of what the wave function charges for being real. Part 10. What if you take the wave seriously? At the 5th Solvay Conference in Brussels in October of 1927, Louis de Broglie stood up and presented an idea that would take 25 years to be taken seriously, and it was, in a sense, the most conservative idea in the room. His proposal was this. Suppose the particle is always a particle. It always has a definite position. It follows a definite trajectory, one path, the way a thrown stone does. And suppose there is also a wave, a real one, a physical one, which does not replace the particle but guides it, pushing it along, steering it towards some places and away from others. Two things, not one thing wearing two costumes, a particle and a pilot wave. If you set it up that way, the double slit result stops being paradoxical. The particle goes through one slit, a definite one, always. The wave goes through both, comes out the other side, interfering with itself, and the interference in the wave steers the particle to land in the bright bands and away from the dark ones. Run it many times with slightly different starting conditions and you get the pattern. No mystery about what goes through which opening. No transformation between kinds of object. Everything has a position at all times. The room did not go for it. De Broglie was pressed hard in the discussion, most memorably by Wolfgang Pauli, who raised technical objections about how the picture handled certain scattering situations. De Broglie could not answer them on the spot. He dropped the idea and did not return to it for over 2 decades. David Bohm revived it, in full and with the technical gaps filled, in 2 papers published in Physical Review in 1952. The timing of Bohm's work is worth knowing. He had been at Princeton, had refused to testify before the House Un-American Activities Committee about colleagues' political associations, was arrested, was acquitted, and lost his position anyway. He wrote the papers that revived pilot wave theory in the middle of being forced out of the country he had done his physics in. He would end up in Brazil, then Israel, then London. What Bohm produced is a complete, working, mathematically consistent version of quantum mechanics. Not an approximation, not a heuristic. It reproduces every prediction of standard quantum theory for the systems it covers. It has 2 equations. The first is the Schrödinger equation, which the wave obeys exactly as usual. The second is called the guiding equation, and it takes the wave and computes from it a velocity for each particle at each moment. And here is the property that makes people fall in love with it. It is completely deterministic. There are no fundamental probabilities anywhere in the theory. Given the exact positions of the particles now and the wave now, the entire future is fixed, down to the last detail. The randomness we observe in experiments comes from the fact that we do not know the exact initial positions, and there is a lovely result showing that if the initial positions are distributed in a particular way, they will stay distributed that way, and that distribution is exactly the Born rule. So the statistical predictions of quantum mechanics come out, but they come out as ignorance rather than as law. John Bell, who is arguably the most important figure in the foundations of quantum mechanics in the second half of the 20th century, admired Bohm's construction openly and repeatedly. And Bohm's theory did something else important. It demolished a piece of received wisdom. Von Neumann had published, in 1932, what was widely believed to be a proof that no hidden variable theory could reproduce quantum mechanics. everyone cited it. Almost nobody had read it carefully. Bohm's theory was a working hidden variable theory that reproduced quantum mechanics, so the proof had to be wrong somewhere, and Bell went and found the flawed assumption. Bell's own famous theorem of 1964 came directly out of that investigation. He was trying to understand what Bohm's theory could and could not evade. There is also something quietly beautiful about what the theory predicts you would see, if you could see it. Bohmian trajectories are calculable. You can compute, for a given experimental setup, the actual paths the particles would take, and when you plot them for the double slit you get a picture that looks like water flowing around obstacles. Smooth streamlines, bending, never crossing, bunching where the bright bands will be and thinning where the dark ones will be. In 2011, a group led by Ephraim Steinberg in Toronto published a result in Science using a technique called weak measurement, which extracts a very small amount of information from each of an enormous number of runs and averages it. What they reconstructed for photons going through a two-slit apparatus was a set of average paths that looked remarkably like those streamlines. Now, that result does not prove Bohmian mechanics. The average quantities it produces can be derived from standard quantum theory without committing to any trajectories at all, and the authors were careful about this. But it is a remarkable thing to have on a laboratory plot, and it is the closest anyone has come to a photograph of the picture Bohm drew. So this is a serious theory, built by serious people, and it takes the wave function absolutely seriously as a physical entity. It is the strongest available version of the claim that the wave is real. Now let us cost it honestly. There are 3 bills, and they are all instructive. The first bill is the one we spent part 6 on. If the pilot wave is a real physical thing, then it is a real physical thing living in configuration space. Bohmian mechanics does not remove the room with too many dimensions. It furnishes it. The wave that guides your two-particle system is an object in 6 dimensions. The wave guiding a dust grain is an object in 10 billion billion. It is a physical entity in a space nobody can enter, exerting influence on particles in a space we can. Some Bohmians accept that and get on with it, but others have made a move that I find genuinely fascinating, and it is one of the most honest things in this whole debate. Detlef Durr, Sheldon Goldstein, and Nino Zhanghe proposed, from the early 1990s, that the pilot wave should not be understood as a physical thing at all. It should be understood nomologically, as law-like. Its status would be closer to that of a Hamiltonian or a Lagrangian or the equations of motion themselves. Real in the sense that laws are real, but not an object in the furniture of the world, not something that exists at a place. Notice what that means. Even inside the tradition that is famous for taking the wave function seriously, serious practitioners have argued that the wave function is not a physical entity. The disagreement is narrower than the popular framing suggests. The second bill is stranger, and it is the one that keeps people up at night. The guiding equation is non-local. To compute how one particle moves, you need to know where all the other particles in the system are at that same moment, including particles a very long way away. Bohmian mechanics does not hide from this. It is honest about it, and after Bell's theorem and the loophole-free experiments of 2015, we know that any theory reproducing quantum predictions has to have something like it. But, at that same moment, is exactly the phrase special relativity refuses to give you. Relativity's central claim is that there is no unique, observer-independent way to slice space-time into moments of now. Different observers moving differently will disagree about which distant events are simultaneous, and relativity says none of them is right, because there is no fact of the matter. The guiding equation needs there to be a fact of the matter. It needs a preferred slicing, a particular way of cutting space-time into moments, singled out as the real one, along which the non-local influence acts. Physicists call this a preferred foliation. It has to be there, and it has to be undetectable, because if it were detectable, we would have found it and relativity would be wrong. That is a heavy thing to carry. It is not impossible. Bohmians have built relativistic versions, including a substantial attempt published by Durr, Goldstein, Norson, Struve, and Zhanghe in 2013, but the structure is required, not optional. You have to add a hidden layer to space-time whose only job is to make your equation well-defined. The third bill is the practical one, and for anyone who cares about actual physics, it may be the worst. Bohmian mechanics works beautifully for systems of a fixed number of finitely many non-relativistic particles. Read that list of qualifications again, because each one is doing work. Fixed number. Particles cannot be created or destroyed. Finitely many. No fields. Non-relativistic. Nothing moving fast. The standard model violates all three. Particles are created and destroyed constantly. Everything is fields. Everything is relativistic. And when you try to carry pilot wave theory over to fields, it strains. And it strains hardest exactly where matter is, because of fermions. Remember the anti-commuting quantities from the last section, the ones with no classical picture. The pilot wave has to live on a configuration space. Fermionic degrees of freedom do not supply a familiar configuration space for it to live on. There is no set of ordinary coordinates for it to be a function of. So the machinery that makes Bohmian mechanics elegant for a few slow particles has nothing to grip on when you get to the electrons and quarks that everything is built from. There are workarounds, they're complicated, they're contested, and several of them end up smuggling stochasticity back in, which, given that the entire appeal was determinism, is a difficult position to be in. 3 bills. A physical object in an unpicturable space, a hidden layer of space-time that relativity says should not exist, and a serious problem with the fields that ordinary matter is actually made of. Every one of those bills has the same line item at the top. Every single one of them is being charged for the pilot wave. Take the wave to be a real physical thing that guides particles, and you owe a configuration space entity, a preferred foliation to make its influence well defined, and a configuration space for it to live on that fermions will not give you. So here is the obvious question, and it is the one this whole video has been walking toward. What happens if you do not pay? Part 11. Everyone pays somewhere. Before we get to the answer, I want to walk you around the room and show you the other options, because it would be dishonest to present one framework as the sole survivor when there are half a dozen serious accounts of quantum mechanics, and every single one of them is held by people who have thought about it far longer than either of us. The rule of this room is simple. Everybody pays. There is no interpretation of quantum mechanics that gets you a comfortable world for free. What differs is which bill arrives. The Copenhagen approach, the one you are probably taught, though it is less a single position than a family of related attitudes associated with Bohr and Heisenberg, pays with silence. It declines to say what the wave function is. It draws a line between the quantum system and the classical measuring apparatus, and treats the apparatus as simply classical, not as a large collection of quantum things. The trouble is that the theory itself does not tell you where to draw that line, and everything in the universe, including the apparatus, is presumably made of the same stuff. The bill here is a boundary that has to be assumed rather than derived, and a refusal to answer the question that everyone actually wants answered. Many Worlds takes the opposite approach and pays extravagantly. Hugh Everett, in his 1957 doctoral work, proposed simply deleting the second dynamical law. There is no collapse. The Schrödinger equation is the whole story, always, everywhere, for everything. When you measure a particle and get one result, the other results also happened. The wave function of the universe branches, and there is a version of the apparatus and a version of you in each branch, each perfectly convinced that a definite outcome occurred. The theory is mathematically clean. It has one law instead of two, and the bill is unimaginable. An ever-branching structure containing every possible outcome of everything, and a persistent, genuinely difficult problem about probability. If every outcome happens, what does it mean to say one of them had a 90% chance? Everettians have worked hard on this. Their critics remain unconvinced. Spontaneous collapse models pay in the most respectable currency available. They change the equations. The best known is the proposal by Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber in 1986, which adds a tiny random localization term to the dynamics. Each individual particle undergoes a spontaneous collapse very rarely. The original parameters put it at something like once every 100 million years. But collapse is contagious in a large object, because the particles in a chair are entangled with one another. One particle localizing drags the whole thing with it, and with something like 10 to the 27 particles in a chair, some particle localizes essentially instantly. Microscopic things stay quantum, macroscopic things do not, and the transition is a real physical process rather than an interpretive stance. What I like about this family is that it is honest enough to be wrong, because it modifies the equations, it makes predictions that differ measurably from standard quantum mechanics. Experiments looking for the tiny heating and the loss of interference these models predict have been running for years, and they have steadily squeezed the allowed parameters into narrower corners without yet closing them off. Quantum Bayesianism developed by Christopher Fuchs and Rudiger Schack among others from around the turn of the millennium, pays by making the wave function personal. On this account, the quantum state is not a description of a system at all. It is an agent's degrees of belief about what they will experience if they act on the world in a certain way. Collapse is then trivially unmysterious, because updating your beliefs when you learn something is not a physical event. The bill is that physics stops being a description of a world independent of agents, which a great many physicists regard as giving up the thing they came for. There is also a relational family, most associated with Carlo Rovelli's proposal from 1996, which pays by giving up the idea of an absolute fact. On this view, a system's state is always a state relative to some other system, the way velocity is always velocity relative to something, with no such thing as absolute motion. An electron can have a definite property with respect to one apparatus and not with respect to another, and there is no further, observer-free fact about which is correct. The appeal is that it takes a lesson we already learned from relativity and applies it again. The bill is that what actually happened stops being a question the universe answers on its own. And I have to mention the strongest published argument on the other side, because leaving it out would be unfair. In 2012, Matthew Pusey, Jonathan Barrett and Terry Rudolph published a theorem in Nature Physics, arguing that, under a set of assumptions about how physical systems can be prepared independently, the quantum state cannot be merely a description of somebody's knowledge about an underlying reality. If two different quantum states could correspond to the same underlying physical situation, they showed, you would get predictions that contradict quantum mechanics. The usual reading is that the wave function must be in some sense physically real. It is a real result and it constrains the space of options seriously. What it does not do is close the question, because like every theorem it has assumptions, in particular an assumption about preparation independence, and a formulation that does not share those assumptions is not obliged to accept the conclusion, but it means that any account claiming the wave function is bookkeeping has to actually engage with this, rather than waving at it. One more thing that no interpretation escapes, and I want to be clear about it because it would be easy to leave you with a tidier impression than the truth supports. Bell's theorem is a theorem. In 1964, John Bell proved that no theory in which distant systems have independent local properties can reproduce the correlations quantum mechanics predicts. The experiments have been done, culminating in the loophole-free test completed in 2015 by groups in Delft, in Boulder, and in Vienna, work that took the 2022 Nobel Prize in Physics for a LAN aspect John Clauser and Anton Zeilinger. The correlations are there. Nature is not locally separable in the way our intuitions demand. Nothing we're about to discuss makes that go away. No reformulation can, because it is a mathematical result about what any theory reproducing the observed statistics must look like. What different frameworks do is describe that non-separability differently, some as a real influence travelling along a hidden foliation, some as a fact about how correlations are structured, some by rejecting the assumption that there was ever a single fixed set of local properties to begin with. The strangeness is conserved. It just moves around. So that is the room. Silence, branching, modified equations, personal states, and a theorem saying the world does not decompose the way we would like. Every one of them is paying a bill, and every one of the bills we have looked at so far has been generated in one way or another by a single assumption that everyone in the room shares, that the wave function is a thing. So what would it look like if somebody simply did not make that assumption? Not, the wave function is real but weird. Not, the wave function is a guide. What would a formulation of quantum mechanics look like if there were no wave in it at all? And could such a thing even reproduce an interference pattern? Part 12. Take the wave away. The answer I want to give you tonight comes out of a line of work at Harvard, in the departments of philosophy and physics, and it arrived in the literature across a handful of papers, one posted in February of 2023, a companion theorem paper in September of the same year, and a fuller treatment in July of 2025. It is not a fringe project and it is not a finished one. It is an active research program, and I am going to tell you what it says and also what it has not yet done. To understand it, you need one idea from ordinary probability theory, and it is an idea you already have most of. Think about a random walk. A particle sits somewhere, and at each moment it hops to a new place, with certain probabilities for where it goes. That is a stochastic process, a system whose evolution involves genuine chance. Physicists have studied these for well over a century. They describe pollen grains jittering in water, molecules diffusing through a room, prices moving on a market, an animal foraging across a landscape. Now here is the property that almost everybody assumes without ever saying it out loud. In an ordinary stochastic process, you can chop the evolution into pieces. If you want to know the chance of going from A to C over some stretch of time, you can insert an intermediate moment, work out the chance of going from A to each possible middle position B, then from each B to C, and add up all the roots. The whole journey is the sum of its parts. That composition rule has a name, the Chapman-Kolmogorov relation, and processes obeying it are called divisible, or Markovian. They are memoryless. Where the system goes next depends only on where it is now, not on how it got there. That assumption is so natural it is invisible. It is how we think about everything that unfolds in time. The story from Monday to Friday is the story from Monday to Wednesday, plus the story from Wednesday to Friday. And here is the move. Suppose it is not true. Suppose you have a stochastic process where the evolution from the beginning to the end genuinely cannot be sliced into intermediate conditional steps. Not, it is hard to slice. Not, we do not have enough information to slice it. Structurally cannot. The journey from A to C over that stretch of time is a single, unbroken, indivisible whole, and there is no consistent way to insert a moment in the middle and ask what the probabilities were there. Such processes are called indivisible. They are non-Markovian in a strong sense. They carry a kind of memory of the moment the system was last conditioned that cannot be repackaged as a chain of local steps. And the technical result at the heart of this program is that this class of processes stands in exact correspondence with quantum systems undergoing unitary evolution. Not analogy, not approximation, an exact, provable correspondence running in both directions. Take an indivisible stochastic process, and you can construct from it a Hilbert space, a state vector, a unitary time evolution, and all the standard quantum apparatus. Take a quantum system, and you can construct the process. They are two descriptions of the same mathematics. There is a detail inside that correspondence which is worth pulling out, because it explains something that has bothered people for 100 years. Remember the Born rule, the instruction to take the wave function's value and square its magnitude to get a probability. In the standard formulation that rule is bolted on. It is an extra postulate, not derivable from the Schrödinger equation, and generations of physicists have found that unsatisfying. In this framework, it is not a postulate. The processes involved have transition probabilities that are, by construction, the squared magnitudes of the entries of a unitary matrix. That is what a unistochastic process is, and it is where the correspondence gets its grip. The squaring is not an interpretive rule imposed from outside. It is what falls out when you write the probabilities down. The most mysterious instruction in the textbook turns into a consequence of the setup. Sit with what that means for a second, because the consequence is the whole reason we are here. If quantum systems can be described completely as indivisible stochastic processes, as systems that have definite configurations at every moment, hopping between them according to laws that simply cannot be broken into steps, then the wave function is not needed to say what is happening. It is not part of the description of the world. It is a piece of extremely convenient mathematical machinery, useful for calculating in exactly the way that a ledger is useful for running a business without being one of the things the business is made of. The Hilbert space, the state vector, the wave function, all of them become, in the program's own phrasing, convenient mathematical appurtenances. You can write them down whenever you like. You never have to believe in them. Follow one electron under this picture and notice what changes and what does not. It leaves the source. It is somewhere, always somewhere, a definite place, the way a stone is somewhere. It moves. It arrives at the barrier and it goes through one of the two openings, an actual one, not both. It continues. It lands on the screen and leaves a dot, and the dot is where it was, because it was always somewhere. Now try to ask the question that has broken a century of intuitions. Where was it halfway through? And the framework does not evade you, does not tell you the question is meaningless, does not lecture you about the limits of language. It tells you something more interesting. The law that carried it from the source to the screen is not built out of a chain of halfway points. There is no intermediate conditional step to hand you, because the process does not decompose that way. The journey is one thing, not a sequence of things you could interrupt, and the strange feeling you get when you hear that is not the feeling of a paradox. It is the feeling of finding out that a question you thought was basic was quietly assuming something about time that nature never agreed to. That does not mean the process can never be conditioned. It can. There are particular moments where the slicing is legitimate, where you genuinely can insert a break and start the probabilities afresh. Those are the moments that correspond to what the textbook would call a measurement, and this is a rather elegant inversion of the usual story. In the standard account, measurement is a mysterious extra process that intrudes on the smooth evolution and does violence to it. Here, measurement is simply one of the places where the evolution happens to be divisible, where the joint is, where the process can be cut. Measurement stops being an intrusion and becomes a feature of the structure. And the reason a measured double-slit experiment loses its bands is not that observation destroyed a wave. It is that conditioning the process at the slits changes which process you are running. So what about the interference pattern? Because that is the whole game. If there is no wave in the room, something has to explain the bands. The answer is that the bands do not require a wave. They require a probability distribution with the right shape, and an indivisible stochastic dynamics generically produces exactly that. Run the process many times, let each run deposit one dot where the particle happened to land, and the accumulated statistics come out banded. The interference is a property of the distribution, not evidence of something rippling through the apparatus. And now the callback, which is the whole point of having spent part 1 in that dark room. You never see the wave, you see dots. We said that at the start as an observation about the limits of the experiment, a slightly frustrating fact about what the apparatus can show you. It is not that. It was never that. On this account, the dots are not the shadow of a wave you cannot see. The dots are all there ever was. There is nothing hiding behind them. The wave was a description of their statistics that we mistook for a description of their cause. Now let me be straight with you about what this costs, because I promised that everybody pays and I am not going to make an exception. The bill here is determinism. This framework is fundamentally indeterministic, and it says so plainly. The randomness is not our ignorance of hidden initial conditions, the way it is in Bohmian mechanics. It is written into the law. The universe, at this level, genuinely rolls dice, not because we cannot see the mechanism, but because chance is what the dynamics is made of. If you are hoping physics would eventually reveal a clockwork underneath, this framework says no. That is a real cost, and some physicists will not pay it. The second cost is conceptual. Indivisible processes are strange objects. A law that cannot be decomposed into intermediate steps is not something most physicists have a comfortable picture of, and building intuition for it is genuine work. You're being asked to trade one unfamiliar thing, a wave in a space with more dimensions than there are stars, for a different unfamiliar thing, a kind of unsliceable wholeness in how systems evolve through time. Whether that is a good trade is a fair question, and reasonable people will answer it differently. But look at what falls away when you make it. There is no pilot wave, so there is no physical object living in configuration space. The room with too many dimensions is not a place where something real is happening. It is a coordinate system for a ledger. There is no guiding equation, so there is no requirement for a preferred foliation of space-time. The hidden layer that Bohmian mechanics needs and relativity denies. There is no wave function needing a configuration space to live on, so the fermionic obstruction that makes pilot wave theory struggle with electrons and quarks is not an obstruction, because there is nothing there to obstruct, and there is no collapse problem, because there is nothing to collapse. Learning where a particle is updates the ledger, and ledgers are allowed to update. Every one of those bills we tallied in part 10 had the same line item at the top of it. Remove the item, and the bills go with it. So here, finally, is the answer to the first half of the question in the title, stated as plainly as I know how. The wave in quantum physics, the Schrödinger wave function, the PSI, the thing in the equation everyone has seen on a t-shirt, is not a physical object. It is not a disturbance in anything. It is not spread through the room you are sitting in. It does not go through both slits, because it does not go anywhere. It is a mathematical device for keeping track of probabilities, living in a coordinate system built for that purpose, and the reason nobody has ever detected one is that there has never been anything there to detect. That is not physics giving up. That is physics handing back something it had been quietly assuming. But it leaves us with the harder half of the question, and I've been holding it since the first sentence. If the wave is bookkeeping, what is the world actually made of? What is real? Some of that answer we already have in hand, and to get the rest of it, we have to leave particles behind entirely and go somewhere much larger. Part 13. The Infinite Room. Everything I have described so far applies to particles, fixed numbers of them, moving around, landing on screens, and if that were the end of the story, it would be a nice piece of philosophy with limited consequences, because the universe is not made of fixed numbers of particles moving around. The universe, as far as we can tell, is made of fields. So the honest question is whether this framework can make the crossing, and the honest answer has two halves. The obstacles that stopped everyone else are absent, and the terrain on the other side is the hardest in physics. Start with why the obstacles are absent. Remember what stopped pilot wave theory at the water's edge. It needed a configuration space for the wave function to live on, and fermionic degrees of freedom would not supply one. That is a problem about where to put the wave. If there is no wave, there is nothing to place, and the problem does not arise. Remember that it needed a preferred foliation to make the guiding equation well defined. If there is no guiding equation, there is no foliation to hide. The obstructions were not obstacles in the terrain. They were consequences of the vehicle. The recipe for the crossing is stated simply enough. Where the particle version has particle positions as the degrees of freedom, the field version has localized field intensities. The strength of the field, here and here and here. Those become the configurations. You apply the same indivisible stochastic laws to them, and the machinery runs the way it ran before. The framework's own literature describes this as straightforward in principle. In principle is doing some work in that sentence, and I want to be honest about how much, because this is exactly where popular accounts of new physics tend to oversell. Here is the terrain. A quantum field, at the simplest bird's-eye view before any of the sophisticated machinery is brought in, has a degree of freedom at every point of space. Not a large number of them, not an astronomically large number, one at every point, and space has infinitely many points, uncountably many, between any two of which there are infinitely many more. Remember the room with too many dimensions, the one we walked into in Part 6. A hydrogen molecule needed 12 directions. A dust grain needed 10 billion, comparable to a decent fraction of the stars in the observable universe. That was the small version. The room a quantum field lives in has a direction for every point of space. There is no counting it. There is no number of stars to compare it to. The astronomical case was the tame one, and I want to stress, because it matters for where we land, that these fields are not abstractions of the same kind we have been arguing about. They are the real ones. We have measured their consequences directly, in ways that are hard to explain away. The electromagnetic field's ground state, empty space with nothing in it, is not quiet. It fluctuates, and if you put two uncharged metal plates extremely close together in a vacuum, the fluctuations between them are restricted compared to the fluctuations outside, and the plates are pushed together by the difference. Hendrik Casimir predicted this in 1948. It was measured with precision by Steve Lamoureux in 1997, and the force is small but perfectly real. At a separation of about 10 nanometers, it can amount to roughly 1 atmosphere of pressure. Empty space pushes. That is a field doing something you can put on a scale. Then there is the field that got its own decade of headlines. The Higgs field is not a metaphor for anything. It is a field filling all of space, and the reason we believe in it is that the Large Hadron Collider produced its excitation, the Higgs boson, announced on the 4th of July 2012, at a mass of around 125 giga-electron-volts. That announcement was the confirmation of a field, found by making a lump in it and photographing the lump's debris. Everything we have discovered about the fundamental furniture of the world in the last 50 years has been a field, and every one of them lives in 3 dimensions of space and 1 of time, right here, where you are. This is the underlying source of quantum field theory's mathematical difficulty, and it was not a minor inconvenience. For a couple of decades it looked like it might be fatal. Calculations produced infinities. Straightforward, unignorable, answer is infinity infinities, in quantities that experiments measured as perfectly finite numbers. The technique developed to handle them, renormalization, worked spectacularly and was regarded by several of its own inventors as an ugly trick. Dirac never accepted it, and Feynman, who won a Nobel Prize for work built on it, called it a shell game and hocus pocus in print. Kenneth Wilson changed how everybody thought about that in the 1970s. His insight was that a quantum field theory should be understood as an effective description, valid down to some scale and no further, with the infinities being a signal that you're asking the theory about distances where it was never going to apply. That reframing turned a scandal into a signpost, and it is why physicists stopped losing sleep over renormalization. It works, and now we understand why it works. But the mathematical situation underneath is still genuinely unresolved, and here I want to tell you something that is not widely known outside the field. None of the quantum field theories that make up the Standard Model has ever been constructed rigorously. Not one. In the mathematician's sense, writing down an object and proving it exists and satisfies the axioms the theory is supposed to satisfy. There is at present no interacting quantum field theory in 4 spacetime dimensions that has been shown to exist. Simplified versions in 2 and 3 dimensions were constructed in the 1960s and 70s by James Glim and Arthur Jaffe among others, and that was real and hard-won work. The 4-dimensional case, which is the one we live in, has resisted every attempt. The difficulty is formalized in a Clay Millennium Prize problem, the Yang-Mills existence and mass gap problem, one of 7 questions carrying a $1 million prize, of which only one has been solved since they were announced in the year 2000. Yang-Mills theory is the mathematical structure underlying the strong nuclear force. Nobody has proved it exists, and it is worse than that, in an interesting way. Haig's theorem, published in 1955, shows that the interaction picture, the standard calculational scaffold that essentially every practical quantum field theory calculation is built on, cannot exist in a mathematically consistent form under the usual assumptions. Physicists use it constantly anyway, and it produces the electron's magnetic moment to about 12 significant figures of agreement with experiment, which is the most precise confirmed prediction in the history of science. Take a moment with that combination, because it is one of the strangest facts in modern physics. The most accurate prediction ever made by human beings was produced by a calculational method that has been proved not to rigorously exist, inside a theory nobody has shown to be mathematically well defined. It has been that way for 80 years, and physics has been fine, because the answers keep coming out right. So when I tell you that extending this new framework to quantum field theory is described as straightforward in principle, that phrase is carrying an honest warning rather than a boast. In principle means the specific roadblocks that stop the alternatives are not present. It does not mean the road is built. Whether the reformulation makes any of quantum field theory's mathematical difficulties easier or harder, or leaves them exactly where they were, is an open question, stated openly in the program's own papers as work for somebody to do. Possibly somebody watching this. I find that a more interesting place to be than a finished theory would be. This is what live physics actually looks like from the inside, a result that is proved, a reformulation that is exact, an extension that is sketched, and a frontier that is honestly labelled as a frontier. But we did not come here for a research program. We came for an answer to a question in 6 words. If the wave is not real, what is? Part 14. What it really is. Let us go back to the dark room one last time. The apparatus is still running. The vacuum pump is still humming. Somewhere in the building it is very late, and the screen has been accumulating landings for hours now. Thousands of them. Tens of thousands. Each one a small localized arrival at one place and nowhere else. The bands have long since emerged. If you stand back, you can see them clearly. Bright, dark, bright, dark. The signature everyone knows. And now you know what you're looking at. You're looking at a histogram. You're looking at the shape a very large number of separate journeys made, piled on top of each other. Every mark on that screen was a particle arriving somewhere definite, and nothing in the room between the source and the screen was ever spread out, rippling, or in 2 places. You never saw the wave. You saw dots. There was nothing else to see. So here is the answer, in full, to the question we started with. The wave in quantum physics is not real, in the specific sense that the Schrödinger wave function is not a physical object. It is not a disturbance in a medium, because there is no medium. It is not in the room, because it does not live in 3-dimensional space at all. It lives in a coordinate system built for tracking arrangements, whose size grows with the number of particles you decide to include. Its values are complex numbers with an imaginary component that appears on no instrument ever built. It is required to sum to 1, which is the fingerprint of a ledger rather than a substance. It has never been detected in a century of the most sensitive experimentation humans have ever performed. And on this account the reason is the simplest one available. There is nothing there to detect, And what it really is, the second half of the promise, is bookkeeping, a device for keeping track of probabilities, enormously useful, mathematically beautiful, entirely dispensable, the most sophisticated ledger ever written. But I want to be very careful about what that does and does not take away from you, because a claim like this can be heard as nihilism, and it is the opposite of nihilism. Plenty is real. Start with the obvious one. Field waves are real. Everything we built in Part 3 stands untouched. Light is a genuine disturbance in a genuine field, propagating through the space you occupy. The warmth on your face in the sunlight is energy that crossed 93 million miles to get there. The magnetic field in a hospital scanner is a real configuration of a real field, tens of thousands of times stronger than the Earth's, and nobody has ever collapsed one, and nobody ever will, because that is not the kind of thing it is. If your system is made of fields, you will see wave behavior, and it will be real wave behavior of the ordinary kind. Not one word of this video was an argument against those. Particles are real, and they are somewhere. On the account we have been following, an electron has a definite configuration at every moment. It is not smeared. It is not in two places. It went through one slit, an actual one, and it landed where it landed because that is where it was. And probability is real, in a much stronger sense than most people mean by the word. Not real, as in a measure of our ignorance, the way the odds on a horse are. Written into the law, the dynamics is made of chance the way Newton's dynamics was made of force. If this is right, then the answer to the oldest question in the neighbourhood, is the future already written, is no, and not because we cannot see the writing. What is not real is the ripple. The picture almost every one of us was handed. Something spreading through the room, going through both openings, meeting itself, and then gathering into a point the instant somebody looked. That picture was assembled out of two different objects that share an English word, and it has been doing 100 years of damage. I should also say clearly, because I would rather you trusted me than agreed with me, that this is one framework among several and it is not settled. The correspondence is a proved mathematical result and nobody disputes the theorem. What people dispute is what to make of it, whether the reformulation is the right way to think about the world or a very interesting alternative coordinate system for the same physics. There are excellent physicists who will tell you that the wave function is as real as the electromagnetic field, and who have arguments for it that we walked through, and who are not going to be talked out of it by an evening's video. What I hope you take from this is not a verdict. It is a distinction, the one between the two things called waves, because that distinction is not controversial at all. Everyone agrees on it. It is simply not said out loud often enough, and almost never said in the places most people learn their physics. It also has a practical edge that is easy to miss. Every time you hear that a quantum computer works by trying all the answers at once in parallel universes, you are hearing the ripple picture again, wearing a different hat. The people who actually build these machines will tell you that is not how they describe what they do. They talk about interference of amplitudes and about arranging a computation so that the wrong answers cancel and the right ones reinforce. That is a statement about the structure of a probability calculation, not about a wave sloshing through a chip cooled to 1/100th of a degree above absolute zero. The clearer the distinction gets, the less magical and the more buildable the technology becomes, which is in general how physics has always paid its way. I keep coming back to how ordinary the cause is. A word got reused. In 1926, an equation was written for a new kind of mathematical object, and because its one-particle case happened to have 3 dimensions and its solutions oscillated, it was called a wave, the same word already in use for the disturbance in a field that Maxwell had described 60 years earlier. 2 objects with almost nothing in common got one name, and the name carried all the intuitions of the older, tangible, physical one into a place where none of them applied. And out of that came the popular impression that reality does not exist until it is observed, that consciousness makes the world solid, that matter is really just waves of energy that intention can reshape, that the universe is fundamentally unknowable and physics has proved it. Books, films, an entire commercial genre, and a general public feeling that the ground underneath everything is fog. 100 years of argument about the nature of reality, conducted by some of the most careful minds of the 20th century, generating libraries of philosophy and leaving a permanent impression on the culture that the world is beyond understanding, may have been, in significant part, an argument about a word. I do not say that to belittle it. The argument was not foolish, and the people having it were not confused in any ordinary sense. The physics is genuinely hard, and the mathematics genuinely does what it does. But there is something moving in the possibility that some of the fog was linguistic rather than physical. It means the world is less unknowable than we were told. It means the mystery, the actual remaining mystery, is smaller and sharper and more honest than the enormous vague one we were handed. And there is a real mystery left. I want to name it precisely, because I would rather leave you with a good question than a false ending. Nobody has finished this. The correspondence is proved, and the extension to fields is stated in principle and not yet carried out. No interacting quantum field theory in 4 dimensions has ever been shown to rigorously exist. And until that changes, every account of what quantum theory means is being written on a foundation nobody has poured. Bell's theorem still stands, and the correlations between distant measurements are still not something any of us has a comfortable picture of. The strangeness does not vanish. It moves. And whether the trade this framework asks for, give up determinism, accept a kind of unsliceable wholeness in how things unfold through time, is the right trade, is a question that will be argued for years by people who understand it far better than I do. Those are good questions. They are much better than the one we were given. So the next time you see the animation, the glowing ripple flowing toward the barrier, splitting, passing through both openings, spreading out on the far side and collapsing into a bright point the moment the eye appears in the corner of the frame, you will know what you're watching. It is a beautiful piece of animation. It is a picture of 2 different things wearing the same name, and one of them was never in the room. What was in the room was an electron going somewhere, the way things do. There is something restful in that, I think, and I did not expect there to be. We are used to being told that the closer you look at the world, the less sense it makes, that underneath the solid table and the steady light, there is a fog of maybes waiting for somebody to look at it. That story has been repeated so many times it has become part of the background of the culture, a low hum of the world being fundamentally beyond us. And it may simply not be so. There may be no fog. There may be things, in places, moving according to laws that involve genuine chance, and that do not decompose the way we assumed time decomposes, which is strange certainly, but strange in the ordinary way that gravity is strange, or that the speed of a light is strange. Strange enough to be worth a lifetime, not strange enough to make the world unknowable. The electron went somewhere. It always went somewhere. The room was never full of ghosts, just a screen full of dots, gradually making a shape that nobody had to be there to see.